So welcome everyone to this GC3 webinar entitled Green Chemistry, Benign by Design. I'm Susky Van Bergen, GC3 Education Project Lead. This webinar is part of the GC3 Education Webinar Series, which is being designed to be a webinar-based green chemistry and safer alternatives training curriculum for GC3 members and other companies. For this webinar, we are excited to present Dr. John Warner. John is the founder of the field of green chemistry and is widely considered one of the world's leading experts in designing safer products and processes. In 2007, he launched the Warner-Babcock Institute for Green Chemistry, which works closely with industries to provide green chemistry technologies for the marketplace. There he serves as President and Chief Technology Officer.
Along with the Warner-Babcock Institute, John co-founded the nonprofit Beyond Benign and serves as the chair of the board of directors for this organization.
He has won numerous awards for his contributions to academia and to green chemistry, including the 2004 Presidential Award in Science Mentoring and the 2014 Perkin Medal. He also has published over 200 patents, papers, and books. This webinar will provide an introduction of green chemistry, including examples of the principles in use and the nexus between green chemistry, chemical policy, and sustainability. And with that, let's get started. Welcome and thank you, John.
Hi, thank you for having me on board. It's a pleasure to be here. I'm looking forward to giving this presentation and want to thank the GC3 organization for allowing me this opportunity. Obviously, I have been, at this for a very long time, for a very, very long time, well over 25 years now, and so sometimes I've been doing it so long that it's hard for me to go back and say, what is green chemistry, and start from the beginning. I think it's very useful to do that. And so anyone who's heard me speak before, there's going to be some slides and some discussion that's going to be old hat, but I've also put in some new things to try to help people understand green chemistry and perhaps answer some questions that have evolved over the years, and do the best that I can. I'm hoping to finish the presentation fairly quickly so that we have time for questions. And so essentially what I'm going to try to do is go through green chemistry and put it in a context for different people along the supply chain to get a different perspective and understand how it all fits together. So first, to begin with, let's start from the very beginning here. We live in a society that has a lot of questions about safety, toxicity, and environmental implications of the chemistries, the products that we're working with. You can't open up a newspaper, turn on the internet, listen on the radio, and not hear about molecules that are dangerous, something being very toxic, some molecule hurting people, something being scary, something being dangerous, something being toxic, and it's just over and over. We're being inundated with all this scary negative stuff. I kind of joke in a half-hearted way that it's almost like the carnival game Whack-A-Mole. That game in which the little animal comes up and you hit it with a hammer, and then another little animal comes up and you hit it, and they get faster and faster. It almost feels as if these issues that we're addressing are like that, and ironically, what is the mascot of the American Chemical Society but a mole? And so in a weird and twisted way, we are playing whack-a-mole with chemicals all the time. We hear about brominated flame retardants, whack. Then we hear about phthalates, whack. And then we hear about bisphenol A, whack. And by the time we wrap ourselves around one issue, another issue has popped up. And we start to wrap ourselves around that one, but another one pops up. And it's exhausting because they're coming at us far faster than we're able to address them. And we're left with this sense of uncertainty. There's some people telling us that this is all a bunch of nonsense, and of course this is all hype, and there's no real problems. And then there are people that are terrifying us, telling us, no, these are serious problems that are challenging humanity and the very survival of our species. And we're left in the middle, breathless, holding these little hammers, not knowing what to do, where we are, what's the right thing to do. And sadly, it's not a game. This is real life. And we need to really step back and understand in a better way what's going on. So I feel, from my perspective, that maybe we're asking the wrong questions, that we keep asking, is this molecule toxic? Is this molecule going to hurt us? What should we replace this molecule with? Which are very important questions. But at the end of the day, there's a more fundamental question, and that more fundamental question is, why would a chemist make a hazardous material in the first place? Let's take it as a given that if I want to make a red dye, and I want to make the red dye stick to a fabric, and I want a red dye not to fade in the sunlight, I don't want it to be toxic. I don't want it to have environmental issues. So if but obviously we have red dyes that are potential carcinogens that have different problems with them. The bigger question is, why are we in a situation where that happens in the first place? And so maybe while we're focusing on how we make molecules, there's a higher order question in what is in the toolbox of a chemist? What is their training that makes this a problem in the first place? And that if we can focus on that very fundamental question, maybe a lot of problems get solutions. So I'm just going to jump to the punchline here. In the United States. Now, the United States is one country in a very big world, and there's a lot of wonderful universities and countries with amazing science programs. I'm from the United States, so I know the United States. In the United States alone, every year we graduate about 15,000 undergraduate degrees in chemistry. We graduate about 3,000 master's degrees in chemistry, and about 3,000 doctoral degrees in chemistry. So about 20 to 21,000 individuals every year receive some degree from a U.S. university to go and practice chemistry, whether it's in academia or in some company. In 2004, more women became chemists than men. And so there is an interesting, people don't fully appreciate that. So one must ask, what could be more important to the field of chemistry than understanding issues of reproductive hazards, of toxicity, of environmental issues? Obviously, with 21,000 practitioners of chemistry every year being made just in the United States, certainly this must be at the top of their list. If I'm going to be a chemist, I should know about toxicity and environmental impact. Well, interesting enough, if you look at all the universities in the United States, and you look at the graduate and undergraduate programs and look at the classes that you are required to take to get a degree, you will be shocked perhaps to find that to get a degree in chemistry, no universities require any demonstrated knowledge regarding toxicity or environmental impact. That should startle you. Think about it. The very people who know how to make molecules, who are going to create the next generation products, for some weird reason, don't have training in toxicology and environmental impact. I'm not saying that the departments don't offer these classes, but they're elective classes for people who have some particular interest. But for the vast majority of chemists who are destined to go out and work in the world creating next generation products, it just doesn't exist. But this is not some part of an epic battle of good and evil. And that's where we have to really recognize this isn't some good, bad, evil thing. It's just a weird thing that has happened in the evolution of chemistry and science education. Now, we can despair and say, oh my God, this is terrible, or we can realize that because of this absence in the education system, there's a path forward. And that's where we should all be very hopeful, because if students aren't learning about toxicity and environmental impact, how in the world can we ask them to make safe products? So essentially, the way I look at it is the following, okay, and this is very new material for me. So I'm going to try this out on this webinar, so I hope you tolerate this strange way of looking at the world. But essentially, there was a time when we didn't have the word art and science. Was Da Vinci an artist, or was Da Vinci a scientist? Was Galileo an artist, or was Galileo a scientist? It's interesting. People in life were makers of both knowledge and stuff. They made contraptions, but they also philosophically interpreted the world. And then we evolved into these things called science and art. And at that very moment, we started separating these scholars, these thinkers, and we started to break apart those who make knowledge and those who make stuff. And then as we advanced into the 20th century and the university started to apply the reductionist approach, and we had chemistry and physics and biology and all these others, the makers of knowledge and the makers of stuff got further and further away until finally we've separated so much that there are people who are destined to go out and make things, and there are people who are destined to go out and create knowledge, and they don't really live in the same world. And so obviously the makers of knowledge, that tribe, if you will, embraced environmental issues, embraced ways of measuring toxicity, embraced the understanding of the world around us, whereas the makers of stuff came up with new ingenious ways of doing things. And so the coursework, the curriculum necessarily kind of separated from each other. And so those few people who were learning about toxicity and things like that were certainly not in the business of making products. And so it's not that this knowledge didn't exist, it's that this knowledge was considered separate. And obviously there's only so much you can put in a curriculum. My friends in academia will say, well, gee whiz, we have so many classes already, how can we add more? But really, from my perspective, one way of looking at green chemistry is to bring those two tribes back together and realize that not only is there a moral and ethical responsibility to understanding these implications when you make something, but there's obviously an economic benefit as well. And so this is a new slide that I've used to try to explain why I feel this isn't some epic battle of good and evil, but an aberration of the way science has evolved over the last couple centuries. So that's where green chemistry comes in, is that, if anyone's familiar, I'm not going to, in this talk here, talk about the history of, working at Polaroid and inventing a technology and, going to the EPA to discuss regulatory issues where, Paul Anastas and I joined forces to write this book on green chemistry. I'm assuming that that's something that's, if you don't already know, it is Googleable. So I'm not going to waste your time with that. But the point is that green chemistry was invented, if you will, to reconnect that vast body of knowledge of science that was learning about environmental health issues and toxicology and connecting them with the very people who were inventing next generation materials and products. And so that's where green chemistry came from. And the 12 principles of green chemistry is the scientific breakdown of ways in which a scientist who is in the business of inventing something can anticipate the issues downstream. And so that's the point of green chemistry, is saying, well, gee whiz, if no one has the right training and someone is about to invent a product that is ultimately going to show up in some shelf somewhere, and they don't have the best of formal training to prepare them, what is a way for them to approach it? And so essentially the 12 principles of green chemistry try to subdivide the issues of making things more sustainable in the language of a chemist or a molecular scientist. The attempt here wasn't to serve, marketing or serve, people that are on the other side of the supply equation, but it was really designed for those people that were making the molecules. Because my point was that around 1990, when green chemistry really became created and we started to really do this, there were plenty of people talking about sustainability. There were plenty of people talking about impacts of human behavior and materials on the environment. That was a well-established thing. But what Paul Anastas and I realized was that the people getting degrees in chemistry, the very people that understood molecular structure, weren't part of that discussion. And so what needed to happen is we needed to get something into the curriculum, into that body of knowledge that those who called themselves chemists could embrace as part of who they were. And so green chemistry was developed and designed to speak to the design scientist who's in the lab, wearing a lab coat, pouring beakers and flasks, inventing the next generation of products. Now, obviously, everyone that follows, the companies that take that technology, the retailers that sell that technology, the customers that use that technology have a role to play in this process. So I'm not saying there's ways that all of society touches on this, but at the end of the day, the fundamental basis of green chemistry is inventing the product to do the right thing in the first place, because that's where we run into problems. Is if a product is invented that has negative impacts but is out on the marketplace, economically that becomes a nightmare to deal with. Obviously we have a moral and ethical responsibility to deal with it, but it's a heck of a lot easier to, not easier from a technological perspective, but better for society if we just don't generate the hazardous products in the first place. So my definition of green chemistry from an operational perspective, the way I look at green chemistry is I say that green chemistry has to have something about it that is more environmentally benign than some incumbent technology. Okay? And so it's got to be better for the environment. It's got to be less toxic. But that's not enough, because if we just have hypothetical solutions that aren't being sold, that are not successful in the marketplace, we actually achieve nothing. And so not only does it have to be environmentally benign and better than the incumbent technology from a toxicological perspective, it's got to have superior performance. And it has to have superior cost, because we cannot, no one is going to buy a product that doesn't work just because it's more sustainable. And nobody's going to, some people will pay a premium, but there's certain vast unfairness if we're going to say that sustainable products are for the wealthy and that the economical ones, sorry, can't do it. And so really, from a green chemistry perspective, my thought is that the product should sell itself absent of the environmental benefit, that people should want it because it performs better and has better cost, and oh, by the way, it's better for the environment and less toxic. Now, I want you to think about that for a second. If you accept my definition that it's got superior performance, it's got superior cost. Now, when I say cost, I mean from a manufacturing perspective, from capital outlays, all of that, and it's better for the environment. Can there be a barrier? Is there any inhibition for that being successful in the marketplace? And I would argue if you truly address performance and cost, there are no barriers except for the invention in the first place. And that's where, in my opinion, we need to be focusing a lot of our attention, is how do we invent products? Because if we can get something that has got superior performance, superior cost, and oh, by the way, is better for human health and the environment, we got a winner. So the way I look at it, and again, sadly, these numbers haven't changed in the last 10 years all that much. But if you look at all the products available to society today, the ceiling tiles, the carpeting, the clothing, the electronics, all the things that we make, I would argue maybe 10% escape scrutiny from some group. That 90% of the things that we're interacting with, some organization, some group of people are very concerned. They may be toxic, they may be using non-renewable resources, they may have a lot of energy in the manufacturing. Something in the sustainability discussion isn't quite right for 90% of the things that are out there. Now, if we do, and we have a moral and ethical responsibility to do so, if we do an alternatives assessment and look at what else is out there to accomplish the tasks that we want to do, I feel today in 2015, we might accomplish success 25% of the time. There may be something that moves the ball forward a little bit in one of these areas. But today in 2015, I still feel 65% of the solutions haven't been invented yet. So it's not that company that's saying, screw it, we're not going to do it. It hasn't been invented. Companies get it. If I can have something that has superior performance, superior cost, and oh, by the way, is better for the environment, wouldn't that be cool? But unfortunately, we haven't invented them yet. And that's a super important thing. No matter how strongly you yell and scream, make a better product, if the people making the product don't have the skills to make it, you can't make it. And so that's an important perspective that I want to wrap up, to address a little bit more. So let's use, I have no claim to some gifted insight. So let's make it very clear. As a disclaimer here, I've lived my life. I've had a unique life. I've worked in industry. I've worked in academia. I've been involved in government policy. I'm an entrepreneur, worked with investors. And so I've kind of touched all the different aspects of the chemical enterprises. I have a view. I don't claim it's the right view. I don't claim it's the only view. But I have a view. So when I talk about how green chemistry fits into the bigger picture, please understand I'm not so presumptuous as to believe I have some gifted insight. It just works for me. And so I'll share it with you, and hopefully there's some value for me doing so. So the way that I look at it, and the reason that this is so upsetting to me in a way is because you go to the green chemistry website at the EPA, they actually state on the website, green chemistry is also known as sustainable chemistry. And I typically drop in the floor in the fetal position and cry like a baby when I read that, because I don't feel that. Now, that doesn't mean it's not true. The world has a right to define things the way they want. Who the heck am I to say otherwise? But just to be clear, I see green chemistry as not being synonymous with sustainable chemistry. Let me explain how. So from my perspective, sustainability is a super umbrella concept, which essentially you can use it to prefix any concept. We could talk about sustainable economics. We could talk about sustainable agriculture, sustainable education, sustainable business, sustainable chemistry, engineering, you name it. We can talk about doing something in a more sustainable way. When it comes to sustainable chemistry, there are many aspects of sustainable chemistry. For example, chemicals policy is part of sustainable chemistry. Remediation technologies is part of sustainable technologies. Exposure controls are parts of sustainable chemistry. Green chemistry, I see it as a subset of sustainable chemistry. Water purification is an important sustainable chemistry. Alternative energy, and this you can imagine a whole bunch of others. Now, here's the point. You can have a solar panel that generates electricity, and we all absolutely agree that is a sustainable chemistry technology the world needs, alternative ways of making energy. But what green chemistry really focuses is not on what the technology does, but what the technology is made of. So the difference between green chemistry and sustainable chemistry is that green chemistry looks at the building blocks. So you can have a sustainable chemistry solar-powered technology, but if you're using toxic materials to make the solar panel, if the material is going to be a nightmare when it's end of use and you got to put it into some landfill and nobody wants it because of the toxic components, it may still be a sustainable technology, but it isn't a green chemistry technology. And that's the distinction, is that green chemistry is agnostic to the application. It looks at the materials, and this is really important because it doesn't care about intended use or inappropriate use. Green chemistry is looking at the materials and saying, are the building blocks of this thing safe for human health and the environment, whether it's used appropriately or not? That is the goals of green chemistry. So it looks at the building blocks. It looks at the solvents. It looks at the catalysts. It looks at the feedstocks. It looks at the toxicity, the persistence, the energy use. I have a bias. There are 12 principles of green chemistry, so I'd argue there are 12 ways of breaking this down. But again, the important thing to remember is that if you're describing the chemistry in its use, that is an important thing to do, and we need to, in society, assess chemistries by how they're being used. I'm not saying that's not important, and sustainable chemistry takes into account the use of the product. Green chemistry doesn't. Green chemistry says if you have an electric cord to a product in your house and your child chews on that electric cord, green chemistry says that child shouldn't get sick from some material leaching out of it. Whereas intended use, you could just say don't have the child clue on the cord. And of course we should. We should be good parents doing that. However, green chemistry dreams of a world in which chemists have not only designed things for the anticipated use, but for the unanticipated use. Because if you think about it, in that top discussion that I had when I listed all of the, this chemical is disastrous, you hear about this explosion, you hear about this fire and this thing here. When we really have problems is when chemistry goes astray because of unintended use, not just intended use. So we chemists have a moral and ethical responsibility to design the chemistry to work under the real world conditions, not just in some hypothetical perfect conditions. Because really, at the end of the day, when we think about where do these products come from, we turn molecules into materials. We call that basic research. We turn materials into components. We call that applied research. We turn components into devices. We call that development. And we turn devices into products, and we call that manufacturing. Now, this has been around for hundreds of years. Companies have been manufacturing things. What is required to do it well? Well, to do this well, you need to look about performance. You got to look at cost. You got to look, hey, wasn't that my definition of green chemistry? Interestingly enough, when you really look at green chemistry, it isn't really any different than the way we've been doing things all along. It's just adding into the equation the environment and asking ourselves, where did those molecules come from? Did they come from renewable or depleting resources? At the end of the product's life, is that going into a landfill, or is it going to decompose into innocuous byproducts when we manufacture it, when we sell it, when we use it? Who is the only person who can truly mitigate the implications of the chemistry in these products? The person who designs it in the first place. So green chemistry says, let's put the skills into the hands and the minds of the men and women who are inventing the technology to anticipate all of this. Okay, and so there has been some confusion in the interpretation of green chemistry as a policy. Now, the way I look at this equation, so I look at this picture on this slide, going from molecules to products, and say to myself, this is kind of like an equilibrium. We constantly want, to be making new products. And I say that chemicals policy is on the demand side of this equation. And it's absolutely essential. We need to have strong, good, effective in renewing our whole approach to chemicals policy at all times. And it's a super important thing to be demanding safer materials and safer products and coming up with policies to ensure that that demand is ever present. But as I said before, if the people making the product don't know how, you can demand all you want and you can't accomplish it. So green chemistry isn't saying it is better or separate from chemicals policy in the long run, but it's different in that it's on the supply side. It is saying, okay, as chemicals policies get released, do we have the skill set of the designers, of the people that are making the products? Do they have the skills and the abilities to address the chemicals policies? Because if we don't have that skill set, the chemicals policies can't work. And so that is the unmet need that I feel in around 1990 timeframe. The aha was, oh my God, although we've done a lot in chemicals policy and the Pollution Prevention Act was passed and all that, there had been no effort on looking at the molecular level science to address it. Think about it. In sciences, we love our subdisciplines, right? There are thousands and thousands of journals of everything you can possibly imagine. The journal of whatever, red textiles, the journal of hydraulic fluids, the journal of this, that, and the other thing. We subdivide our workshops and textbooks and journals and all over the place. But in 1990, was there a subdivision of people that was sharing thoughts, having workshops, having journals to talk about making things less toxic and less impactful to the environment. And the fact is, no, there was no science to describe that. So there was no place philosophically for scientists to go to publish their work, to communicate, compare notes, and to work the way the science works of incremental improvement, building on itself. So the purpose of green chemistry, first and foremost, was to create a science to deal with chemicals policy, not to replace chemicals policy, certainly not, but to give the designers, the people who understand molecular structure, their place at the table to address these issues. If you're interested in life cycle assessment and analysis and wondering, well, how does this all work with life cycle analysis? What I did was I took each of the 12 principles, there they are in these green rectangles, and then I spread out the life cycle. Going on the left, you see molecules, and on the right, you see the products. Now, obviously, this is really a circle. It's not a line because the products go back, but that would be a very complicated diagram. So I flattened this out. What I did was I took each of the 12 principles and I applied it across the life cycle. Now, here's an important thing to realize. Although the 12 principles apply, in a lot of places, if you're in marketing and you're saying, how can we use the 12 principles of green chemistry in marketing, you can't get them all. There are certain aspects of green chemistry that don't really apply on the marketing side. It's too technical, wonky, and we chemists really do it. But if you're in research and development, that's where all the 12 principles apply. And so green chemistry, obviously all products have to be invented, they have to be researched, they have to be developed. So we all have a place to play in this thing here, but it's important to understand that green chemistry was not created as an evaluation of products. It was created as a research and development tool. I feel that there are many tools available now for us to evaluate products. I won't, and I'm sure everyone on this call understands the great work that some organizations are doing coming up with those things. Again, what I saw missing was the inventors, the people that were developing the technology. So the 12 principles of green chemistry focus on that aspect. And an important thing to understand is that green chemistry is not the birth of ethics. I do not feel that chemists somehow were immoral and acting badly, before green chemistry came along. Of course not. Chemists have always, they have children, they have families, they love the world. This isn't some birth of ethics, but it was an interesting way that we approached it. And what we did is we said, okay, chemistry has to be toxic. It's just one of those things, but the way we're going to deal with it is we'll wear gloves to protect our skin. We'll wear masks to protect our lungs. We'll wear goggles to protect our eyes. We'll install scrubbers and filters and smokestacks to protect the air, the land, and the sea. We can work with toxic, dangerous things because we got it covered because we're going to mitigate exposure. And so essentially the way it works is that risk has two components. It's got exposure and it's got hazard. And prior to green chemistry, we pretty much focused on mitigating risk by dealing with exposure. If you have a toxic material and you stick it in something and make sure it's not going to leach out, and as long as everybody behaves the right way and they do the right thing, we're going to be fine. Well, what green chemistry says is sometimes things go wrong. Sometimes people don't do the right thing, and it's the job of the chemist to look at the intrinsic hazard, independent of how the product is being used, and design at the molecular level structures that create that inherent safety so we're not dependent on exposure. Because every time some disaster happens, I promise you, there was an exposure control conceived of, it just didn't work, or it broke down. And so the ultimate goal here is to have products that survive, in safe ways, regardless of what happens. Now, what's important at this moment for me to talk about, though, is that there is no magic green button. As important and as how passionate we want it so, we cannot snap our fingers and have a green chemistry society tomorrow. It took over 200 years of science and technology to get to where we are today. And we can't just magically invent everything tomorrow. It is going to take decades and decades of time to figure this all out. And no product is going to be perfect. What you have to understand is that if there are 12 principles, and we want to make a safer society, we can't say, let's keep selling the same technology today until we address all 12 principles. Well, there's a lot of human suffering that's going to happen that way. So we need to get into the mode of celebrating incremental improvement. If somebody invents a technology that is less toxic but still uses a lot of energy in the manufacturing process, as long as they're not taking a step backwards, even if they're not addressing everything, we need to celebrate that advance. If then, somewhere else in the globe, someone comes up with a way of using less energy, and then someone else comes up with a renewable feedstock, then we put it together. That's how science works. And so we've got to realize that this is all a bunch of incremental victories, and the enemy of the excellent is the perfect. And so as we look at these hazards, we have to realize that we can't do everything immediately, and we have to be comfortable with the fact that this is going to take time, and we have to come up with a process to motivate and incentivize the incremental. If all we do is reject anything less than perfect, I promise you we will never have perfect. And so think of it from a different perspective, from the costs. All right, if you look at a product and you say, I could have this product consist of all safe, non-toxic materials or hazardous materials. Well, it costs a lot more to store, costs a lot more to transport, treat, dispose, regulatory costs, liability, health and safety, corporate reputation, community relations, employment. It's a hands-down fait accompli. Anyone would rather have a safer, non-toxic, non-hazardous technology, period, assuming it has still superior performance and superior cost. It's just if it hasn't been invented, that's the problem. So here is an interesting graph that I put together. It's a little outdated, and I have to update it. It's a little bit old now, but what we did is we went back to the National Register and we looked at all the environmental laws and regulations imposed by the U.S. federal government over the last several years. We went back to 1870, and you can see that not a whole heck of a lot happened until 1962. Rachel Carson published Silent Spring and the birth of the modern environmental movement, and you can see a change. Okay, so what these blue dots are these are pieces of federal legislation talking about if you're working with this, that, or the other thing, you got to make sure it's not getting into the land, the air, and sea. So all things somewhat related to environmental regulations. Now, we can debate whether the trend is fast enough or not, but clearly there is an unequivocal trend that since the 1960s, there's been a lot more environmental regulations, and those are going to continue to evolve and to come into play. I would argue that the single biggest impediment for a company to do business, or one of the biggest impediments, is understanding this changing landscape. To understand, how do I make a product that is going to be consistent with these things? And the sad reality is that most scientists inventing technologies aren't equipped to address this. So any company looking at this says, okay, from now on, I want all my chemists to only invent non-toxic, environmentally benign products, period. Well, unfortunately, it's unlikely that those chemists have had the right training. So even if they want to, they can't. And so green chemistry has to get embedded into the education system so that we have a generation of chemists. So I look at this and I say, okay, we have a toolbox in the chemical enterprises. Okay, and the toolbox that we have available in the chemical enterprise has a bunch of toolbox draws in it. Okay, we have a draw for carbon-carbon bond forming reactions, oxidations, reductions, hydroxylations, you name it. Now, we can probably make almost anything we can imagine with our chemistry toolbox. There's still some unmet challenges, but for the most part, if we can draw it, it doesn't violate some fundamental law, we can make it. However, if we imagine a green chemistry toolbox where each of those draws are now replaced with technologies that are environmentally benign, non-toxic, and not regulated, as I said earlier, that toolbox is 90% empty. I feel unequivocally that any individual, just for self-preservation reasons, any company for economic reasons, any developing country for obvious reasons, will open the green chemistry toolbox first. It just makes smart business sense. But statistically, odds are that draw is going to be empty. And so what we have as our challenge is how do we get those draws filled? So what a company or an individual or a developing country must do is close the green chemistry toolbox, go to the traditional toolbox, say, how much is it going to cost for my gloves, for my mask, for my goggles? What am I going to pay the lawyers to deal with this? Because you can't stop everything and invent on the fly. That's not the way inventions work. You can't just say next Tuesday at 2:30 I'm going to invent a new material that's less toxic. And so companies have to deal with it because they've got business pressures. They have to get a product out by the next quarter. So we need to find forces in society to enable us to fill the green chemistry toolbox, the universities, the institutions, and the only way that's going to happen is if we all work together to shout in a uniform voice, fill the toolbox, and find not one way, not two way, but infinite ways in which people can participate in filling that toolbox. And so I got although the table of contents looks like a lot, the rest is pretty quick. I want to refine the discussion of product design because I think it's really important for people to understand the challenge that we have at this moment. If I am in the business, and I am, at the Warner Babcock Institute, we invent products. Okay, if I'm going to design a product, I need to know and prioritize the key attributes of the product. Then I have to design some way of evaluating the success while I'm doing my research and development. And then I have to identify solutions where I fall short. And then I have to measure and quantify, the performance of my alternatives to see if it works or not. And obviously, if it's acceptable, I shout, hooray, I make a product and I go to market. Now, here's the problem. As I said before, when we're talking sustainability, we're only going to succeed less than 25% of the time. And so when we get to this point, we have to instead go back and do something else. We've got to invent a new technology. And I think it's important for people to understand who aren't in the business, what does it mean to invent a new technology? All right. And so we're going to have to do this circle. So let's go to this again and look at it from if we're just looking at classical performance and cost, let's say I'm being asked to make a paint that doesn't fade. All right. Well, I need to find what the industry standards are, what the voice of customer is, what's the business economics. If I want to design a plan to evaluate it, so again, going for the paint, is I want it to be stable and light. I want it to be stable to cold and heat. I want it to have the appropriate cost. Those would be key attributes to my hypothetical paint. All right. Now, how am I going to evaluate the success? Well, there are ASTM tests for light stability and heat stability. There may be some in-house historical stuff at my company, or the customer I'm selling it to may be saying, this is the way I want to measure it. And so, for example, Z% fading and Y amount of time, you can read the slide here. I'm not going to read it all, but there's very precise definition of what those attributes are. So then the next thing I do is I want to identify some possible things that exist out there. Obviously some of my suppliers may have some things. Maybe I can do some, product development intelligence. Maybe I can look in the supply chain and figure some things out. And so then I develop some candidate molecules and materials. And let's just call them A, B, and C. Then what I do is I go in a lab and I test them. All right, I can either test them myself, I can ask my supplier, I could pay a third party, and then I get all of these attributes, S, T, U, V, W, X, Y, Z, essentially how do they behave in different things. Then I look at it, I scratch my chin, and I do the in-house R&D, or if it doesn't work, I have to invent a new technology. I can either do it myself, I could have my supplier do R&D, I could ask universities and government to do it, or some third party. And then that's the way it goes. However, this is what we do all the time. But here's the rub. If we now instead add to performance and cost, safety and sustainability, in order to invent something, we have to do the same thing. We can't just say make something safe. We have to get better priorities and attributes. So the regulatory agencies and the NGOs have to step up and help us define what we mean by these. And so it may be we want to look at mutagenicity, endocrine activity, hepatotoxicity, or energy use or renewables use or something like that. Then we have to design the metrics in government agencies and third-party organizations, maybe an Ames test for mutagenicity, maybe a type Ed screen for endocrine disruption, maybe a mitochondrial damage. So we can think of a bunch of assays. And then we identify the alternatives. We do an alternatives assessment to get new materials. And then we quantify the performance. And maybe in addition to the three that I mentioned, government labs can step up and we get new numbers that have to do with the safety and sustainability. And obviously, if something new isn't invented, isn't found, we got to go back to the drawing board and do this over and over. This is how invention works. Now, here's the thing. For me to invent something, all right, it has to be quantifiable. If I'm making a paint that doesn't fade, that means nothing to me. Obviously, all paints fade, so it has to be something else. It has to be achievable. So it's color. I can't say color never fades. That's not achievable. So what I do is I say color can only fade over a little bit over a certain part of time. That's achievable. So then how do I measure it? Okay, I'm going to put it in a device, I'm going to shine light, and I'm going to measure how much it fades after a certain amount of time. That's how science works. I can't invent a paint that doesn't fade if someone doesn't give me this info. I can't just say, hey, does this work? No. How about this? No. I have to have science that I can go in the lab, do an experiment, go try it out. If it works, say hooray. If it doesn't work, go back to the drawing board. The quantifiable, achievable, measurable must be there for me to invent. So therefore, if we're doing this for sustainability and safety, we've got to do the same thing. We've got to come up with the same kind of criteria. Another thing about zero and big numbers. Okay, let's look at this for a second. Let's talk about nothing. Right? This drives me crazy. There are two issues with the use of free and zero. Okay, what does chemical free mean? All right, here are some products. I hope I'm not, making someone mad on this call, but this drives me crazy. People that are putting on their products chemical free, come on now. Water is a chemical, skin is a chemical, spit is a chemical. Everything, if it has mass and we can experience it, it is a chemical. So we shouldn't be using words like chemical free. That is just really treating the public as, very inappropriately. Chemical free has no meaning. But I don't want to talk specifically about that. What I want to talk about, though, is can we ever really have anything free? People may be familiar with the issues around BPA, all right, that there was a lot of discussion about BPA and cash register receipts. Now, here's an interesting philosophical question. Now, I can take a piece of paper, I can put chemistry on it, and I can say I did not add BPA in the coating. But can I say that it's BPA free? There could be trace amounts of BPA that have somehow made it into the paper that I didn't put there that are below my detection limits. We need to realize that saying something is absent from a product can never be real except for the state of science. What do I mean by that? So one way of looking at it is the following. Imagine I have a 55-gallon drum of water, and I put it in, and if you look at a 55-gallon drum of water, do you realize that's like 7 times 10 to the 27 molecules of water? Look at that number with all those zeros. If I were to take a teaspoon of sugar and put it into that drum of water, that's still 8 with 21 zeros after it. I promise you will not taste that sugar in that water. That's pretty dilute, but it's still a lot of zeros after that number. It's actually 1 ppm of sugar in that tank. If I were to take a grain of sugar, just one simple grain of sugar, and say, well, that's almost nothing. Well, actually, that still has 17 zeros as far as the number of molecules, and we're still talking 50 parts per trillion. But look at 50 parts per trillion of sugar still has 17 zeros after it, in a number. If we took a nanogram of sugar, we can't even measure a nanogram. The smallest we can conceive of, that's still 12 zeros. So when we say a product is free of a molecule, All right, it depends on how much we're being able to measure. So right now, what I have in this yellow square, we in science can't measure. So when we say that a product is free of something, we have to be clear to say it's free from our ability to measure. It doesn't mean that someday someone's not going to invent a new test device that is able to measure it better. And that we've got to, as a society, recognize that that's a reality. Because in the room that I'm sitting right now in my office, there's all this air around me. I promise you, almost every nasty molecule we can imagine is in this room, and I'm breathing it. It's just at such a low quantity, we're not capable of measuring it. But if we're going to be rigorous in our language and we say a product is free of something, we got to realize that only means that it's free of our ability to measure. And I just wanted to explain that, so as we do our inventions, we have the language type, because as we go forward and we invent a way to go to these number of zeros, and then we go to these number of zeros, and we go to these numbers of zeros, we're still always going to have some uncertainty. So finally, let me close up by saying, how does this all fit together? For us to invent and design solutions, we need to be quantifiable, achievable, and measurable, as I said. And Typehead is a great example of people trying to do this. Pete Myers and Advancing Green Chemistry and a group of scientists that are on this paper are trying to address exactly this thing around endocrine disruptors. We've got to do this for all different endpoints. We've got to, as a community, start thinking about it. And so I encourage people to look at this as an example of a potential way of addressing these issues. But let's look at it for a second. I drew this invention of a product and looking at sustainability and safety in a vertical way. If you think about it, looking at this process of invention, chemicals policy is at the top. It's defining what it is that we want to do when it comes to safety and sustainability. The field of toxicology and environmental health sciences is the second down, that is working on inventing ways of measuring and understanding the mechanisms. And then alternative assessment is the next level down, that is seeking things that already exist in the market to satisfy that. And then finally, when there isn't an alternative on the market, green chemistry comes in to invent it. No one of these aspects can live on its own. No two, no three. The only path forward is all four of these work together. And so when we talk about green chemistry and getting green chemistry, I'm not suggesting that everybody go and take chemistry classes and put on a lab coat and work in a lab, but they need to understand how all of this comes together. And at the end of the day, if the scientists inventing the technology don't have the skills to make the products, we got nowhere to go. And so, we need to realize that every decision we make, whether we're a purchaser at a retail shop, if we are working at a brand, if we're working at a chemical company, we all have a role to play in all of this. And so, but we can't sit on our hands waiting for everything to be sorted out. We can't. The enemy of the excellent is the perfect. We've got to realize we've got to just do whatever we can in our own little worlds, in our own little environments, and find ways of pushing this forward and collaborating with other people. No one can do this alone. We all have to do our parts together. And so communication, integration, that's why GC3 is such a great organization to be convening and pulling these people together. And so I'm not going to talk about this because we're really running out of time. At my institute, if you go on my website, at warnerbabcock.com, you'll see that my belief is that science and business together come to make prototypes, and they have to have equal emphasis as we invent things. If you just do science without the business, you end up having a commercial nightmare. And interestingly enough, that's where these issues of sustainability and toxicity come into place. So what we have been doing historically is creating incubators that take a prototype and try to drive to commercialization with a prototype. I feel that the success rate of this is not that good, not because the people in the incubators aren't doing a good job, but frankly the prototypes aren't good enough. because there's not enough business built into the prototype, and there's certainly not enough green chemistry built into it. And so what the world needs is not more incubators, but what I call technology greenhouses that pull together the science and business at equal weight and look at the implications to society as the technology's been invented, not afterwards. And that's what WBI is an example, and I'm sure that there are other places that are doing this as well. And in the last 3 months, if people have been paying attention, we've released a hair coloring technology, a recycled asphalt technology, a formaldehyde-free wood composite adhesive, and reuse of ocean plastics with Adidas and Parley as 4 simple examples. Well, not very simple, it's a lot of work, that incorporate the 12 principles of green chemistry for things that are on the road to commercial success. And so this isn't just a philosophy. I would argue that the Warner Babcock Institute is succeeding not in spite of green chemistry, but because of green chemistry. Because if the rest of the world is all taking the same classes, doing all the same thing and going in the same direction, doing anything different is going to give you an edge competitively from an innovation perspective. And what better different than to be focusing on safety and environmental impact? And that's the opportunity. If we all pull together and figure out what our parts are, we can pull this off. And in fact, we are. We should be very, very comfortable with the progress we've made, but we can't rest. There's still a whole lot more to do. I hope this has been useful to you all. Thank you for listening.
We do have a few questions that have already come in. One of them is very specific. So do green chemistry innovations have to have reduced costs, or are the indirect costs sufficiently? If they're reduced indirect costs, is that sufficient?
That's the way I look at that is companies have had to make that decision on new products all the time. They look at a new product, they say, okay, this is a new product. It has benefits. Obviously, if it didn't have benefits, they wouldn't be going through all the problem of having a new product. If they feel the market can bear a higher cost because of those benefits, then it should. If they feel that the market won't bear that cost or would benefit from a reduced cost, then it should. And so if each product, each embodiment of an innovation has its own life today. But what I would say is that it is a big mistake to believe that all green chemistry must be more expensive. I can tell you as a fact that, from my definition, that's just not true. There is no requirement that a technology now is got to be more expensive. Now, one of the issues, and I'm going to expound on this just a little bit because it's important. It's an interesting thing, is that if you go through the history of science, when polymer chemistry became really popular, when catalysis started to become really popular, all through history there have been new emerging technologies that have come on. No one sat around crying in their milk saying, why won't the world appreciate this technology? They rolled up their sleeves and they made better products with the technology. Interestingly enough, I would argue green chemistry is identical in that way. But interestingly, because it has a moral and ethical component, we take one step forward and we start saying, well, gee, the world should do it just because it's the right thing to do. And although I wish we lived in a universe where that was so, we don't. And so from my perspective, the only way we pull this off is if they are better products at better costs that have better performance. It's not a requirement, but it sure makes life a lot easier.
Great, thanks. Another question. You mentioned that green chemistry doesn't work well in marketing areas. So if a company has difficulty in marketing products using green chemistry, how do you see innovation driven by the market?
Because the way I look at it is the following, and it's going to be a little bit of a complicated answer, but it's really important. I am not a good golfer, okay, but my wife is a phenomenal athlete in golf, and so I understand the concept of golf by watching her. I'm laughable, so I get it. Imagine you had 5 golfers and you wanted to evaluate how well they played the game of golf. Well, you could get an Excel spreadsheet out and you could have them all drive. You could have them all putt. You could all have them get out of a sanding. And you could measure some performance and put it on an Excel spreadsheet and come up with some algorithm and say, this is the best golfer, this is the next best golfer, this is the next best golfer. Now, obviously, if you wanted to sell the attributes, come and see the person who has the farthest drive. This is this person. You can see where the communication of these abilities become very, very important to that Excel spreadsheet. But what if you want the golfer to become better? While it's important to know these numbers, they do nothing to make the golfer better. You can yell, drive farther, but that doesn't make them drive farther. You know, if the golfer is going to improve their game, it's how they hold their shoulders. It's how they grip their club. It's how they put their feet on the ground. It's these intangible things that don't fit well in an Excel spreadsheet, but actually get the golfer to be a better golfer. And that's where green chemistry fits in. It's less the ta-da, look at my, my attributes of my product. It's the behind-the-scenes science at the molecular level mechanistically of how to improve the product. Okay, and so that's the distinction that I make. It's not that marketing can't use the 12 principles. There are clever ways, and companies certainly have. So I'm not saying that it can't be done, but the design of the 12 principles with the more subtle behind-the-scenes mechanistic approach of how do you improve. So it's not the noun of what you do, it's the verb of how do you do better. And the 12 principles of green chemistry are designed from that perspective.
Another question, you mentioned that we currently don't live in a green chemistry society, and so what would be your dream team for green chemistry innovation with respect to knowledge and skills?
You know, we need to come up with a really good way of communicating what it means to have sustainable products. I do not feel the way that we've been approaching it now is addressing what society needs. And again, I'm not going to go into this in great detail. I could talk about this for an entire hour. But right now, the best we can do is to make lists of bad ingredients and say to society, we should not use these bad ingredients. Now, I right now believe that's the best we can do, so we have to do that. But that's not getting us to where we need to go. We need to be coming up with a better way of doing this. We have to come up with what are the assays, what are the tests that measure the performance of products, and then start saying, instead of saying, I don't want BPA in this product, we should say, I don't want this product to be an endocrine disruptor. I don't want this product to be a carcinogen. And here are the tests that I want to have done on the product to verify that it's not. Until we pull that together, that's a long job ahead of us. But until we do that, and we're just picking and choosing molecules not to use, that doesn't help the inventors. And so we need to come up with a way of helping the inventors invent the better products. And just saying don't use one molecule, that's why we have such a history of unfortunate substitutions, because our only way of approaching it right now is to tell people what not to use. And so there are many alternatives to a molecule that may be just as bad. And so for my dream is for us to rethink chemicals policy to be more focused on what is necessary to invent the replacement, not just saying what not to do, but helping at a mechanistic level to learn what to do.
If you were to have an innovation and you had, like, for example, a chemist, you mentioned toxicologists, other kind of currently siloed backgrounds that would be useful in that?
Well, almost any thing. It's really interesting. People say, oh, well, I don't do chemistry, so I don't do green chemistry. That's not really, I like, it's kind of an absurd joke, but if someone says, I don't do green chemistry, literally what that means is when they wake up in the morning and they think of what they're about to do that day, they are trying to choose the most toxic and hazardous way of doing things. I'm going to use the most toxic, milk in my coffee. I'm going to use the most hazardous this or that. Now, I got to assume nobody does that. Everybody, just for self-preservation reasons, is going through some mental algorithm to choose the least toxic, the most safe way of doing everything they do in life. The problem is we don't have a skill set to do it well. And so it's interesting, of all the things we learn in school of how to do things, one of the most important thing, how to keep ourselves safe and help keep the environment safe, we really don't have a curriculum to help us do that. So we're bumbling around doing the best that we can. but I would argue everyone intends to keep themselves and their community and the environment safe. We just don't have the appropriate skill set and training to do it.
For you mentioned green chemistry is a design of chemicals that are environmentally benign. How do we define what safe is in the context of green chemistry?
Well, I again, this is and I would love to have an entire hour someday to talk about my views on this. I feel we need to focus on quantitative assays first. We need to, as a community, come up with a bunch of endpoints that we think are important. Hepatotoxicity, ozone depletion, global warming potential, endocrine disruptions, whatever. We make a list of all the endpoints that we think all products should report information around those important attributes and endpoints. Then next, we have to come up with assays and tests that we pretty much uniformly or somehow come to consensus are appropriate. That's going to be hard work. That's going to be a lot of work, and it's going to take a lot of time, but it's no more difficult than doing the molecules by molecule assessment we do now. Instead of evaluating each molecule, if we evaluate the mechanism by which we evaluate molecules, we could have committees putting assays and tests up on a list, and then committees taking those assays down, and we can debate that. Then the next step is we need to be running the quantitative score on those assays of products. Not necessarily get into the good, the bad. No one has to play God and say, that this is safe, this is not safe. But just can you imagine if we had a world in which, if you go to the supermarket and you buy a food, you have to see how many calories, how much protein, how much, carbohydrates. Now, nothing is saying good, bad, or ugly. It's just giving you the numbers. Can you imagine if we had a system in which, in no controversial way, people just reported on the Ames test, it's got a 7.2, on this test, it got a 9.3, and then all the non-government agencies and groups could communicate to the general public and say, never buy a product that has a 7.2 or higher on this assay. Don't buy a product that has a 5.3 or lower on this assay. And the thing is what's really cool is then if we had that quantitative relationship, then designers, inventors would have very precise targets. If I'm going to spend money and time inventing a product that just uses the word safe, who am I going to use as their definition? And so if there is if these NGOs are saying 7.2 is unacceptable, well, I know if I can go in the lab and invent something with a lower number than 7.2, I can evaluate the investment that would be required and decide if it's worth me doing. But absent of that piece of information, all I can really do is pay lawyers to fight the regulations and to fight the claims of good, bad, and safe because there's no scientific framework for the conversation.
What's the role of, for example, brands and retailers? Do you have suggestions on different activities to best aid in the advancement of green chemistry?
Yes. My answer will be yes, of course. Each brand is different. Each brand has a different relationship with its supply chain. Each brand has a different relationship with its customers. I think right now, historically, what has happened is we have the separation that the brands are in the front saying we want sustainability, and that somehow we've vilified the chemical industry as not providing the brands with appropriate replacement materials. And I think the brands have to step up to the plate and recognize they have more of a role to play there than just to continue to sell the products that they sell and say if only the suppliers would change what they're giving us. That there has to be a closer partnership and a closer responsibility that the brands must take. And so until they do that, there's a problem. And so I think that the brands have to be working closer with their suppliers and sharing in some of the investment that is required to invent the new technologies. They can't have it both ways. They can't say we're going to continue to sell the stuff that's unacceptable until someone else invents. They have to take a more active role, and many brands are, but not enough of them.
Thank you. So thank you, everyone, for attending. Thanks again, John.
You're welcome. Thank you.